In this lecture, we're going to be talking about short circuit analysis. So in simple terms, a short circuit occurs when conductors are shorted between each other or to ground in a three-phase power system. And so fault studies deal with calculating bus voltages and line currents during faults and are very important since they will tell us how to set protection systems to detect faults. So let's first define a few things for the types of faults that can occur in a power system. And just a side note, I'm going to be using the terms short circuit and faults interchangeably. Because typically when you say a fault in a power system, what you mean is a short circuit in the power system. And so there are different types of faults that you can have in a power system. The most severe one is often what's called a three-phase fault, where you have basically all three conductors get shorted together. And they may be shorted or not to ground. That doesn't really matter for a three-phase fault, as we're going to explain in a future lecture. But basically we have all three phases, A, B, and C, shorted together, which is obviously not something that you want in a power system. Because remember that the voltages across each conductor has the same magnitude, but it's shifted by 120 degrees from each other. So if you short them out, it's essentially shorting out a voltage source, which causes a spike in current. And so this is what a three-phase short circuit would look like. Now you may also have what's called a line-to-line, or also called sometimes a face-to-face fault. And let me just write it down over here. I'm going to say this is a three-phase fault. And this one, it's what's called a line-to-line fault. And sometimes you will hear people say face-to-face fault as well. In this case, line and phase are used interchangeably. Then you may also have what's called a double line and ground fault, where you have two conductors shorted together and also shorted to ground. So this is commonly called a line-to-line to ground fault, or sometimes people call them also double line to ground. So double line to ground fault. And then lastly, you can have a single phase to ground fault. So basically only one phase or only one conductor gets shorted to ground. So this is called a single line to ground fault. Now of course, when you have line-to-line faults or double line to ground or single line to ground faults, you can have all sorts of combinations. So in this case I drew an A to B fault, but you can also have a B to C fault or a C to A fault. So you can have all the combinations there. And then likewise, same thing for the double line to ground or line to ground fault. In this case I drew an A to B to ground fault, but you can also have a B to C to ground or C to A to ground fault. And the same thing for a single line of ground. In this case I drew a to ground fault, but you can also have a B to ground fault or a C to ground fault. Now a three-phase fault is what's called a balanced fault. And it's called that for obvious reasons. If you short all three phases together, then the resultant fault currents and voltages in the system are going to continue to be balanced, just like they were before the fault. Of course, the magnitudes are going to change, but they're going to be balanced, meaning that the magnitudes are going to be the same between each other, but shifted 120 degrees. Now, when you have line-to-line or double line to ground or single line to ground faults, all of these faults are what's called unbalanced faults. I'm going to say all of these are unbalanced faults. And so the analysis of a balanced fault, which is what we're going to take a look at first, is pretty straightforward because the system is still balanced, you can analyze currents and voltages just like you would in any other three-phase circuit. Now when you have an unbalanced fault, the system is no longer quote-unquote balanced, meaning that the magnitudes between the phases are not going to be the same. So for example, if you had an A to ground fault, you're going to have a spike in the A phase current, but you would not on the B or C phase current. So in other words, the magnitudes are no longer going to be equal to each other. Same thing happens for a line-to-line to ground fault or a line-to-line fault. Essentially, the magnitudes of the voltages and currents become unbalanced, meaning their magnitudes are not equal to each other anymore, and they're not spaced 120 degrees apart from each other. So these types of faults require a little bit more complex analysis, and we're going to take a look at that in the next section of the course, where we're going to introduce the concept of symmetrical components, which is a technique that's used to analyze unbalanced systems. But for this section, we're going to take a look first at three-phase faults, just so that we can start getting familiar with short circuits and fault studies before we dive into more complex analysis of unbalanced faults. In this lecture, we're going to be talking about balance or three-phase faults. So following up on the previous lecture where we defined the types of faults that can happen in a power system, recall that a balance or three-phase fault happens when all three conductors are shorted together. Now they may be shorted to ground or not, in addition to being shorted between each other, but that doesn't really affect the current magnitudes or the voltage magnitudes. And so a fault can be what's called a bolted fault, meaning that all three conductors are shorted together through a 0 ohm impedance. So basically we have a perfect metallic connection between all three phases. This right here would be called a bolted fault, which again means that there's no impedance in between the short circuits. So you can see here that I drew A to B and B to C as a straight line. There's no impedance in between. Now likewise, a fault could be what's called a resistive fault, where you have some resistance in between the short circuits between the conductors. So this would be R, or rather, let me just say Z, because it could really just be an impedance. So this is what's called a resistive fault. For obvious reasons, there's an impedance in between the conductors. Now that may be a couple of things. Usually when it's a three-phase fault, is the arcing resistance of the arc between conductors. So if you have a transmission line that's spaced out by a couple meters or several feet between each other, if they short out together, all three of them, and they have some resistance, it's probably just an arc between the conductors, meaning it looks like a lightning strike. Basically, the insulation of the air separating the conductors break, and you'll see a spark in between the conductors. Now, I mentioned before that for a three-phase fault, it doesn't really matter if, in addition to being a three-phase fault, the short is connected to ground or not. And that's because, again, for a three-phase fault, we have a balanced condition. So let's say that our fault currents were 1 per unit at 0 degrees on A phase. And let's say that B phase then, again, because this is a balanced condition, needs to be 120 degrees apart from the A phase. And then same thing for the C phase. So let's say now that in addition to being shorted with each other, this was shorted to ground. Then that would mean that the currents flowing through A phase, B phase, and C phase would be flowing through this path to ground. However, because we have a balanced condition, then the ground current, which I'm going to call I sub G, again, it's going to be equal to IA plus IB plus IC, which is going to be equal to these three right here, is going to be 0 amps because they're balanced. So they're going to cancel each other out. So that's why I'm saying that it doesn't really matter whether a three-phase fault is shorted to ground in addition to being a three-phase fault, meaning all the conductors shorted together. That doesn't make it more severe. It doesn't really matter because this is a balanced condition, so there shouldn't be any current flowing to the ground, even if it's shorted to ground. So I just wanted to point that out because that's a normal misconception that if you have a three-phase to ground fault, that's somehow more severe than a three-phase fault. It's not. It's the same thing as far as impedances go, which means that the fault currents would be the same. So whether a three-phase fault is shorted to ground in addition to being a three-phase fault doesn't really matter. Now, as I mentioned, because this is a balanced condition, we can analyze a fault current in a per phase basis, just like we've done for other power system analysis. So for example, let's say that we have this system over here where we have one generator that is operating at 1 per unit voltage, and it has a series impedance of J.1 per unit, and then that's connected to a bus that's connected through a transmission line to another bus that has a load on it. Now let's say that a three-phase short circuit happens on this bus. So we're going to say that at some point this switch closes and it shorts out all three conductors to ground at this bus. Now when that happens, we would then have the following circuit. So I'm going to say when the fault happens, we go from this circuit to this circuit. So essentially we have now this path to ground. Now notice that I left out the remaining part of the circuit, and that doesn't really matter because there's no source over here, so that's not going to contribute to our fault current, and because current flows through the path of least resistance, or least impedance in this case, then no current is going to keep flowing to the remainder of the circuit because this part right here is shorted to ground. So this is essentially a zero impedance connection to ground, which means that all the current that flows from the generator is going to go down to ground. There's nothing going to be flowing over here because, again, the current flows through the path of least resistance, or in this case, least impedance. And so now that we have this condition, we can simply say that the fault current, which I'm going to call IF, is simply going to be equal to the voltage of the generator over the impedance to the short circuit, or to the ground, which in this case is just this impedance. So for this example, the fault current would be the voltage, which is 1 per unit at 0 degrees, over the total impedance to ground, which in this case is just this impedance. So over J 0.1 per unit. So our fault current for this example would be 10 at minus 90 degrees per unit. So again, this is a pretty straightforward example, but I just want to mention that because three-phase faults are balanced, we can analyze it using normal circuit analysis like we've done before. Now, of course, in this case, I'm referring to A phase on the voltage. So really, a more accurate thing to say would be to say that the A phase fault current is this current, 10 at minus 90 per unit. And then the B and C phases are going to be separated by 120 degrees from that. So we get minus 90 minus 120, that would be an angle of minus 210 degrees. And then C phase is going to be at positive 30 degrees. Alright, so next let's take a look at more complex examples of three-phase faults. Alright, welcome back. So for this example, we're going to be doing a balanced fault example. So basically a three-phase fault. And for the example, we're going to be using the following power system. So we're going to have in our power system a system equivalent over here. So this right here is going to be our system, which is going to be at 100 MVA base. So this again is the data for our example power system. So the source impedance X sub S is equal to 12%, and it is at 230 kV. So it's a system that operates at 230 kV nominal. So this is the data for our system equivalent for the example power system. Now connected to that, we're going to have a transformer over here, and then we're going to have a bus. So that transformer is connected to a bus. We're going to call that bus the bus X. Then that's going to be connected to a feeder, and then we're going to have another bus over here, which I'm going to call bus Y. And then on that feeder there's a load. So this is a symbol for a load, and that load is 50 MVA at 0.8 power factor. Now the data for the transformer So the transformer is going to be a delta on the high side and grounded Y on the low side. And again, this is the transformer. And the data for that is also a 100 MVA transformer, so the same rating, or rather the same base power as the system. And it's going to be a 230 kV, so 230 to 13.8 kV. And it's going to have an impedance X sub T that's equal to 8%. And then lastly, our feeder, we also of course need the data for that. So that's going to be a 35 MVA base. So in other words, the information that we're given is on a 35 MVA base. And it's going to be operating of course at 13.8 kV. So the same of course as the low side of a transformer. And then it's going to have an impedance, which I'm going to call ZXY, since it connects buses X and Y. That impedance is going to be 0.1 at 85 degrees. And all of this of course is in per unit. So now what we need to do is we need to take a couple steps to be able to calculate the fault current for a three-phase fault at bus Y. So we're going to have a fault again over here. So that's what we're trying to do for this example. So let me actually move this up a little bit. And I'm going to say, well, step number one, and let me write it over here. Step one is going to be convert everything to a common base. So convert to a common base. And what I mean by that is that notice again here in the data that we've been given for the power system that the system and the transformer have 100 MVA as the base power, but the feeder has a base power of 35 MVA. So this impedance over here is in per unit, but that's in per unit of 35 MVA, not 100 MVA as the system and the transformer. So that's important because of course we can't use then this per unit because it's on a different base than the system and the transformer. So we need to convert that impedance to a same, or rather to the same base as the other stuff in the power system. So in this case, we're going to pick 100 MVA as our power base, since both the transformer and the system have 100 MVA base, and we're going to convert the feeder to 100 MVAs. So let's see how we can do that. Again, we've mentioned this before, but recall that the equation that we can use to convert impedances that are in one base to another base is this following equation over here. So Z new is going to be equal to Z old times the new base power, so ASB new over SB old, so the old base power, times VB old, so the old base voltage, over VB new, so the new base voltage squared. So in other words, what this equation says is to get a new impedance on a different base, you need to plug in the old impedance over here, and then SB new, SB old are the two different base powers, and then same thing for VB old and VB new, so the two different base voltages. So in this case then, to get ZXY, the feeder impedance in 100 MVA base, we would take the impedance, so 0.1, so this number over here, so that's 0.1 at 85 degrees, so 0.1 at 85 degrees. And then we'll multiply that times the new base, which is going to be 100 MVA, divided by the old base, so 35 MVA, times the new, or rather the old base voltage over the new base voltage. Now in this case, they're both going to be 13.8 kV. So 13.8 over 13.8 squared. All of this, of course, is going to be equal to 1. So now from here, we can calculate our new base impedance, which is going to be equal to 0.286 at the same angle, so 85 degrees. And now again, this impedance is, let me just write it over here, at 100 MVA and 13.8 kV. So essentially all we did was convert this impedance, which was at 100, or rather at 35 MVA base, and we converted it to 100 MVA base. So now we have everything in the system in terms of 100 MVA as the base power. So we have everything on a common base. So now step 2, and let me actually switch colors over here. So I'm going to say over here, step 2 now is going to be, well, let's draw our circuit. So draw the circuit. So again, coming from this system over here, we're going to have the system over here. Then we have our source impedance. So this is going to be XS. Then we have the transformer impedance. So this is going to be XT. And then we have bus X. So this is bus X. Then we have the feeder. And then lastly, we have bus Y, which is where the fault is. So this right here is bus Y. And again, here is where the fault is. Let me use a different color. So here's the fault. So now we can plug in the numbers again. This right here would be Z, X, Y, the feeder impedance. So our source impedance is going to be 1 at 90 degrees. And the reason that that's 90 is because we're taking the terminal voltage, so this point over here of the generator, as the reference. So if that's at 0 degrees, then the generator, this source impedance, or rather this source voltage over here, which is a perfect source, would be at 90 degrees. But again, that's not too important. Angles just matter depending on what you take as a reference. Here I'm taking this point of the circuit as the reference. So that source voltage needs to be at 90 degrees. So then the source impedance again was equal to 12%. We saw that over here at the top. So 12% of course in per unit would be 0.12. So this is equal to J, since it's a reactance, so J 0.12 per unit. Now the transformer is 8%, so that would be J 0.08 per unit. And then lastly, the feeder, we just calculated over here, that's 0.286 at an angle of 85 degrees. And that's of course all in per unit. So now we have our circuit from which we can calculate the fault current, which is going to be the fault current that flows this way. So this is going to be IA. So now in step 3 then, let me move this up a little bit more and let's switch colors again. Let's do red. So step 3 now is going to be simplify. So simplify the circuit and calculate current. Circuit and calculate the current. Alright, so what I'm saying here by simplify is, well, we know that the fault is over here. So then I can just simply add all the impedances to make my calculation a little bit easier. So what I'm going to do then is I'm going to redraw the circuit and I'm going to say, well, I'm going to have the system over here. This again is my system. That's 1 at 90 degrees per unit. And now I'm just going to have one impedance. And then I'm going to put the fault over here. So this impedance Z is essentially going to be the combination over here of the system impedance, the transformer impedance, and the feeder impedance. So Z is going to be equal again to XS plus XT plus ZXY. So all the three impedances combined together. And if I add up those numbers, which again are over here, so if I add up all those numbers, I get that impedance is equal to 0.486 at an angle of 87.057 degrees, and that's again in per unit. So now from here I can easily calculate the fault current, which is this fault current here, IA, and that's simply going to be, of course, we know that V equals IZ, so then that means that I is equal to V over Z. So the current is equal to the voltage divided by the impedance. So I then, IA, would be equal to the voltage. So in this case, 1 at 90 degrees per unit divided by the impedance, which in this case is this impedance that we just calculated. So 0.486 at an angle of 87.057 degrees, and that's in per unit. So now if we calculate this, we get that IA is going to be equal to 2.058 at an angle of 2.943 degrees, and this is in per unit. So this right here is our result. Now we can have one more step which would be to convert from per unit to actual quantities, of course, if we needed that. So I can say then over here, let me switch colors again. Let's do green now. So I'm going to say then step 4 is now going to be convert to actual quantities. So in this case, again, remember that, let's say recall that the base current IB is equal to the base power SB divided by the square root of 3 times the base voltage. So then for this case, again, our base power was 100 MVA, so 100 times 10 to the 6 for MVA divided by square root of 3 times the base voltage, which is 13.8 kV. So 13.8 times 10 to the 3. Now one point that I want to make here is that, again, we calculated the fault current in per unit. So now when we convert back to actual quantities, it depends where we want to see that current. In other words, if we want to see the current that flows through the high side of a transformer, so this part over here of the system, then we would use 230 kV as the base voltage. Now if we want to calculate the fault current on the low side, so this right here, then that would be a 13.8 kV, which is what I'm calculating in this example. Now again, if you want to see what the fault current would be on the high side of the transformer, then you would use the 230 kV base voltage. So just one point that I wanted to make. So again, here now we have our base current. If we calculate this, we get that the base current would be equal to 4,183 at an angle, or rather 0.698 amps. So now we can get that IA in actual quantities, so in amperes instead of per unit, would be the per unit value, so 2.058 multiplied times this number. So let me just write it over here. So 2.058 at an angle of 2.943 multiplied times the base current. So in this case, 4,183.698 amps. So that gives me that the fault current IA would be equal to 8610.05, and then the angle stays the same, so 2.943 amps. So this right here is the fault current in amps on the 13.8 kV part of the system. Now remember again that we said that for a balanced fault, essentially, as the name implies, the fault is balanced. So that means that IB, for example, and IC for an ABC rotation system, they're going to have the same magnitude, so 8610.05 for both, 8610.05, but the angles are going to be shifted by 120 degrees. So IB is going to be minus 120 and IC is going to be plus 120, again for an ABC rotation system. So the angle for the B phase then is going to be minus 117.057 degrees, and this is again in amps, and IC is going to be 122.943 degrees. So now we have all three phase currents. So we have IA, IB, and IC. Again, because this is a balanced fault, all of them have the same magnitudes, and the angles are shifted by 120 degrees. All right, welcome back. So let's take a look at another example to just solidify our knowledge of balanced faults. So for this example, we're going to have a slightly different power system. So we're going to have a generator instead of a system. Let me just draw it over here. We're going to have a generator over here. This is going to be a generator with the following data. So it's going to be 200 MVA power. The synchronous reactance is going to be XS, is going to be equal to 10%. And this is going to be at 13.8 kV. So now that generator is connected to a transformer, which is commonly referred to as a step-up transformer, since it steps voltage from a generation magnitude to a transmission or distribution magnitude. So here our transformer is going to be a delta Y grounded on the low side, and it's going to have this following data. So this again is a transformer, and it's going to be a 220 MVA transformer, so slightly higher than the generator, and it's going to be a 13.8 to 230 kV transformer, and it's going to have an impedance XT equal to 7%. Now for this example, we're going to connect that to a bus, and we're going to fault this bus over here, so we're not going to have a feeder. Now one thing that I want to mention here is that notice that the transformer has a different impedance than the generator. So again, just repeating the steps that we did in the previous example, we can say, well, step 1 would be to convert to a common base. So convert to a common base. So in this case, I'm going to convert the transformer impedance, which is at 220 MVA as the base, to 200 MVA, which is the base of the generator. So again, using the same equation that we used before, XT new is going to be equal to XT old times SB new over SB old times VB old over VB new, all of this squared. So for this example, again, the voltages are going to be the same, so this is going to go to 1, and then the new reactance XT new of the transformer, again, new meaning we're converting from 220 MVA base to 200 MVA base, which is the base of the generator, to bring them to a common base, is going to be equal to XT old, which was 0.07 times the new base of 200 divided by the old base, so 220. So if we calculate this, we get that XT new is going to be equal to 0.06364 per unit. So 364 per unit. Now step 2, and let me switch colors and let me write it over here. So step 2 now is going to be draw the circuit. So in this case, again, we have generators, so we have the synchronous reactance of the generator, then we have the transformer, and then we have the bus. So we're going to have only 2 reactances over here. So we have the system over here, which again, we mentioned this before, but this is going to be at 1 and 90 degrees per unit, since we're taking the terminal voltage of the generator as the base, or rather as the reference. And then we have the generator reactance, so this is going to be XS, which is equal to J 0.10 per unit. Then we have the transformer reactance, XT, that's going to be equal to J 0.06364 per unit, which we calculated over here. And then we have the bus, which is where the fault is. So this right here is the bus, and we're putting the fault over here. So again, here IA would be flowing this way. And now we have our circuit. So step 3 then, let me move this up a little bit more. And let's switch colors again. So step 3 was simplify the circuit. Now in this case, this is a pretty simple circuit. So simplify the circuit. But again, just to follow the steps, let's go ahead and simplify it. So we're going to have the source. So 1 and 90 degrees. And then we're going to have just one reactance. So we're going to combine here. This reactance is going to be equal to the 2 reactances combined together. So XS plus XT, which is going to be equal to J 0.16364 per unit. And again, we're putting the fault over here. So now, again, IA is over here. Now we can calculate IA, which is going to be equal to 1 at 90 degrees. So our voltage divided by the impedance, so J 0.16364, 16364 per unit. And so if we calculate this, we get that IA, let me move this up a little bit more, IA is going to be equal to 6.11 So 6.11098 per unit. Now the angle here is 0 because we're dividing 90 degrees on the numerator and 90 degrees, essentially J, which is 90 degrees, on the denominator. So they cancel each other out. So this is simply 6.11098 per unit. Now step 4, we mentioned this before again, but let's go ahead and do it. So step 4 is now going to be convert to actual quantities, meaning we're going to go from per unit to amps. So quantities. So in this case, again, the base current is equal to the base power divided by square root of 3 times the base voltage, which in this case we took 200 MVA as the base power. So we're going to have this equation 200 times 10 to the 6 divided by square root of 3, and then the base voltage. So again, that depends on where you want to see the current. If you're trying to get the current on the high side of a transformer, so this right here, then you will use 13.8 kV. If you're trying to get it on this side, which in this case I guess would be the high side of a transformer, and the other side would be the low side since it's a lower voltage. But in this case, again, that would be 230 kV. So it depends where you want to see the fault current result. In this case, I want to see it where the fault is, so on the 230 kV system. So my base voltage would be 230 times 10 to the 3. So again, 230 kV. So that's going to be equal to 502. So 502.044 amps. So now I can say that IA then is going to be equal to 502.044 multiplied times the per unit quantity, which is over here. So 502 times 6 would be equal to 67.98. And again, I mentioned this before, but this is essentially at 0 degrees. Now again, the B and C phase currents, since this is a balanced fault, are going to have the same magnitude, so 67.98 for both. And in this case, we're using an ABC rotation system. So the B phase is going to be lagging by 120 degrees, and the C phase is going to be leading by 120 degrees. And this is not in per unit, this should be in amps. So all of these results are in amps. So now here we have our results for our example power system over here at the top, where we have a generator and a generator step-up transformer that steps up the voltage from 13.8 kV to 230 kV, and then we're faulting the 230 kV bus. So the result, again, is over here. We're getting, because the fault is balanced, we're getting the same magnitude for all three phases. And again, they're balanced, so A phase is at 0 degrees, B phase at minus 120, and C phase at plus 120. And then the magnitudes are the same, in this case, 3067.98 amps. In this lecture, we're going to be talking about symmetrical components. So the technique of symmetrical components is a way for us to decompose a set of unbalanced vectors into a set of balanced vectors. So let's see what we mean by that. Let's say, for example, that we had a three-phase current in our power system that looked like this. So we had A phase somewhere around here. We had B phase, let's say, over here. And we had C phase somewhere around here. And so as you can see, this set is not balanced, meaning in a normal power system that's operating under normal conditions, you would have what's called a balanced three-phase system, where, for example, the three-phase currents would have the same magnitude between all three phases, and they would be spaced out 120 degrees from each other. So that's what we call a balanced three-phase system. Now, we may also have what's called an unbalanced system, in which the magnitudes of the currents and voltages are not equal to each other, and they're not spaced out 120 degrees from each other. And so the reason why the power system may be operating under that condition is because there might be a fault in the system. So during what we call unbalanced faults, meaning single line of ground, line to line, or double line of ground faults, the system becomes unbalanced, meaning that the quantities between all three phases are not the same. So the magnitudes of currents and voltages between the A and B and C phases are not the same, or rather they don't have the same magnitude, and they're not spaced out 120 degrees from each other. So we could have something like this during a fault where the system again becomes unbalanced. And so the technique of symmetrical components basically tells us that we can decompose this set of three-phase vectors into three different sets of balanced vectors. In other words, we can represent this three-phase set of vectors into these sets of balanced vectors. And so these are what we're going to call the sequence components, and they're going to be called the positive sequence, the negative sequence, and the zero sequence here on the right. And let me go ahead and write down what we're going to call each one of these vectors over here. So this is going to be, again, the positive sequence set, but this current right here is going to be what we're going to call I sub A1. And so the number 1 is used for the positive sequence set. And then this right here would be IB1. This right here would be IC1. And then on the negative sequence set, we're going to have a phase rotation that is opposite to what our system is. So for this example, I'm assuming that the system has an ABC rotation. So let me write it over here. This is our assumption for these vectors over here. We have a system that has an ABC rotation. And so the positive sequence set has the same rotation as the system under normal conditions. But the negative sequence set has an opposite rotation. So if we say that our system is an ABC rotation system, then the negative sequence set would have the opposite rotation. So we would have the A phase over here again, and we're going to use the number 2 for the negative sequence set. But this vector right here, instead of being B, is going to be C. So this would be IC2, this would be IB2. So again, basically the negative sequence set has the opposite rotation of our system rotation. Now the zero sequence set is going to have the same angles between all three phases. So we can say that this one at the bottom would be IA, and we're going to use 0, of course, for the zero sequence set. This vector right here is IB0, and this one on the top would be IC0. And so again, all we're doing here is we're decomposing this unbalanced set of vectors into three sets of vectors that are balanced. And so again, we're going to use the number 1 for the positive sequence set, the number 2 for the negative sequence set, and the number 0, of course, for the zero sequence set. And this is pretty typical. This is usually what people use in industry. Sometimes you would see just a positive sign on the positive sequence set and a negative sign on the negative sequence set. But for the most part, people use 1 for positive sequence, 2 for negative sequence, and 0 for the zero sequence. And so again, the concept of symmetrical components is just a mathematical tool that we can use for our analysis of unbalanced power systems, such that we can analyze unbalanced faults, for example. Now we're going to introduce one quantity here, which we're going to call the operator A. And A is going to be equal to 1 at 120 degrees. So 1 at 120 degrees. And this is going to be a useful constant for our definition of symmetrical components. So let's define that first. So the technique of symmetrical components basically tells us that the phase current, so let's say IA, IB, and IC, is going to be equal to the summation of all these sequence sets for that phase. So for example, the A phase current is going to be equal to IA0 plus IA1 plus IA2. So let's write that down over here. When I say, again, IA being the actual phase quantity is going to be equal to the zero sequence current for the A phase plus the positive sequence current for the A phase plus the negative sequence current. And then same thing for B and C phases. So the zero sequence plus positive sequence plus negative sequence. And then for the C, same thing, zero sequence plus the positive sequence plus the negative sequence. So again, we're basically saying we're going to decompose this set into these three sets, and then the phase currents are going to be equal to the summation of the sequence components, such that IA, for example, is equal to the zero sequence IA quantity, the positive sequence IA quantity, and the negative sequence IA quantity. Now in these, again, IA and IB and IC are balanced for the zero sequence, and they're balanced for the positive sequence and balanced for the negative sequence. So let's go ahead and write this down in matrix notation. We can say then that we're going to have IA here, IB, IC, and that's going to be equal to this matrix over here. We're going to say that's equal to 1, 1, 1, 1, A squared, A, 1, A squared times the sequence components. So times IA0, IA1, IA2. So again, the A operator is this operator that we defined over here, and such that if you take the square root of that, you would get that that's equal to 1 at an angle of 240 degrees. So the reason why we can say this, notice that I've written down here IA, IB, and IC, but here I wrote down IA0, IA1, and IA2. I didn't use B or C phases. Is because notice that from here, for example, the B phase on the positive sequence set is lagging the A phase by 120 degrees. So in other words, IA1, it's going to be equal to the magnitude of IA1, of course, at an angle of 0 degrees. That's pretty obvious. We've defined IA1 over here. But then I can say then that IB positive is equal to the magnitude of the positive sequence A phase current. And again, for a balanced set, we're assuming that all the magnitudes are going to be of the same value, but shifted by 120 degrees. So again, we can see that from this vector diagram over here. We can see that the B phase has the same magnitude as the A phase, but is shifted by 120 degrees. Or in other words, it's lagging the A phase by 120 degrees. And then same thing we can say for the C phase. The C phase is going to be equal to the magnitude of the A phase positive at an angle of 240 degrees. And then likewise, we can do the same thing for the negative sequence set. We can say that the A phase negative sequence set is going to be equal to the magnitude, of course, of itself at an angle of 0 degrees. But then we can say that the B phase negative sequence is equal to the A phase negative sequence magnitude shifted by 240 degrees. Because again, on the negative sequence set, we're saying that the phase rotation is opposite to our assumption for this example that it's ABC rotation. So the B phase, instead of lagging the A phase by 120 degrees as in the positive sequence set, is lagging it by 240 degrees. And so for the same thing for C phase, we can say the negative sequence C phase is going to be equal to the negative sequence A phase shifted by 120 degrees. Again, we can see that from this vector diagram over here. And so that's why we can define this matrix over here, where I said IA, IB, IC on this side, and I'm not using B or C here on this side. But it just comes from the fact that I can see from my balance set over here that in the positive sequence set, B is lagging A by 120, and C is lagging A by 240. And then likewise for the negative sequence, the C phase is lagging A by 120 and B is lagging it by 240 degrees. And so again, using these operators that we've defined over here, we can get this equation over here. Now these currents over here are what we're going to call the phase currents. In other words, the phase currents are going to be the actual currents that are in the power system. And these, we're going to call them the sequence currents, or the sequence components of the currents. So that's just a common nomenclature that's used in industry. Again, when we say phase currents, what we mean is the actual currents in the system. And when we say the sequence currents, what we mean is the decomposed balanced set of those phase currents. Now this matrix over here comes pretty useful, so we're going to call that the A matrix, or also called the symmetrical components transformation matrix. So let me just write that over here, symmetrical components transformation matrix. Now we can see from here that we can also define, let's say, the phase currents. So I'm going to call that I subscript ABC for the phase currents. Is going to be equal to this matrix, the symmetrical components transformation matrix, times the sequence components. And I'm going to abbreviate that I sub A 0, 1, 2. Then likewise from this matrix we can get the opposite. So if we know what the sequence components are, doing this we can get the phase currents, but we can also do the opposite. If we know the phase components, then we can calculate the sequence components using the following equation. So I can say that IA, which again is this vector over here for the sequence components, it's going to be equal to A inverse times the phase vector, this one over here, so IABC. So using these two equations we can go from phase components, if we know that, we can calculate the symmetrical components or the sequence components vector, or if we know the sequence components vectors, we can calculate the phase components as well. And so we can go back and forth from those. And one last thing that I want to say here is, let's define this inverse, or rather let's calculate the inverse of this matrix A. If we do that, we would get that that's equal to 1/3 times the following. So 1/3, 1, 1, 1, 1 A squared A, or rather just A over here, A squared, 1 A squared A. So you can see that if we calculate the inverse of this matrix over here, we would get that that's equal to 1/3, and then we're going to swap the A squared with A's over here. So we get 1, 1, 1, 1, 1, 1 on the first column and the first row, and then we're going to swap A squared with A in these four terms over here. So I get, instead of getting A squared, A squared, I get A squared, and A over here. So again, I just want to write that down just so that you have these two matrices handy if you want to go from phase components to sequence components, or if you want to go from sequence components to phase components. Alright, so next let's talk about the sequence components of voltages in a unbalanced power system. In this lecture we're going to be talking about the positive, negative, and zero sequence voltages in an unbalanced power system. So in the previous lecture we talked about the symmetrical components technique, and we referred to the currents in that example. But I just want to show that the same thing applies for voltages as well. So during an unbalanced condition, which is usually a fault in the power system, the voltages are not going to be balanced anymore. So the magnitudes between all phases are not going to be equal to each other, and they're not going to be spaced at 120 degrees from each other, like you would have in a balanced power system that's operating under normal conditions. And so remember that we said that the A matrix, which we called the sequence components or symmetrical components transformation matrix, was equal to the following. So we said that was equal to 1, 1, 1, 1 over here, 1, A squared, A, and A squared. And of course we said that the A operator was equal to 1 at 120 degrees. And we said that, if we take the square of that, we would get that A squared would be 1 at 240 degrees. And then we also calculated the inverse of that matrix, and we said that A to the minus 1, or in other words, the inverse of the A matrix, was equal to 1/3 of basically the same matrix, but we're going to swap the A squares with A's. So we would get 1, 1, 1, 1 over here, 1, A squared, and A over here. And so just like for the currents, we can say that the phase voltages, which I'm going to call the vector VABC, is equal to the A matrix times the sequence components. So I want to say that that's equal to A times VA0, 1, 2 for the sequence components. So in other words, what this means is the following. So we're going to say that the vector of the three-phase voltages, so VA, VB, and VC, is going to be equal to A, which again we've defined over here. So I get 1, 1, 1, 1, 1, A squared, A, and A squared, times the vector of the sequence components. So VA0, VA1, and VA2. Or we can also write this in terms of the actual equations. So then we can say that the VA, or the A phase voltage, is going to be equal to the summation, as we would expect, of all the sequence components for the A phase. So that would be equal to VA0 plus VA1 plus VA2. And then likewise we could calculate VB and VC. We would get that VB would be equal to VA0 plus A squared VA1 plus A VA2, and then VC would be VA0 plus A VA1 plus A squared VA2. So again, I just want to show that the same thing that we discussed for the currents and the symmetrical components technique also applies to voltages, and really it applies to any set of unbalanced vectors. It just happens to be that a power system is a good application where it's helpful to decompose a set of unbalanced vectors into a set of balanced vectors. Now again, we're going here from, we're assuming that we have the sequence components and then we're using the A matrix to get the phase components. But we could also go the other way around, where we could calculate the sequence components. So I'm going to call that VA0, 1, 2 as the inverse of the A matrix times the phase components, A, B, C. So again, this would be saying that the sequence components VA0, VA1, VA2 is going to be equal to A to the minus 1, which we calculated over here. So let me actually make more space here. 1/3 times this matrix over here. So 1, 1, 1, 1, 1, A squared, A times the phase components. So VA, VB, VB, and VC. And then likewise, we can just write this out. We can say that VA0, VA1, VA2 would be equal to, for the A0, we're going to get 1/3 VA plus VB plus VC. And then here 1/3 VA plus A times VB plus A squared times VC. And then lastly, for the native sequence, we would get VA plus A squared VB plus A VC. So again, we're just using the symmetrical components technique to go from phase quantities to sequence quantities and vice versa if we needed to. And the reason why we're doing that is because during an unbalanced condition of a power system where the voltages and currents become unbalanced, decomposing that into a set of balanced voltages and currents makes the analysis of the power system during those conditions a lot easier, as we're going to see in future lectures. In this lecture, we're going to be talking about the positive, negative, and zero sequence currents and how we can use them to calculate three-phase power. So we know, of course, that power equals voltage times current. So we can also say that the three-phase power, or rather the three-phase apparent power, which I'm going to call S sub 3 phi, is equal to this matrix VABC transposed times the matrix IABC conjugate. So all this is saying is I'm going to multiply the A phase voltage times the A phase current, B phase voltage and current, and C phase voltage and current, which of course is going to give me the three-phase apparent power, because remember that the three-phase power would be the summation of all the individual phases. So if I calculate the A phase power, B phase power, and C phase power and add them all up together, I would get the three-phase power. So that's what this equation right here is saying. Now what I want to do for this example is I want to see how we can calculate the three-phase power using the sequence components and not the phase components. So let's see how we can do that. We know that the vector that has the three-phase voltages, so this vector over here, is going to be equal to the A matrix times the sequence components matrix, which again we called VA012 transposed. And then we're going to do the same thing for the current. So the phase currents vector, this one over here, is going to be equal to A times the sequence components currents. And that's of course conjugate. And so again, the T over here means transposed, which we need to use in this equation to get the apparent power. And so this of course is going to be equal then to A transposed times this vector for the voltages, VA012 transposed, times A conjugate, and then the sequence vector for the current, so IA012 conjugate. So what I'm doing here is I'm taking the transpose of the A matrix, transposition of the voltage matrix, and then taking the conjugates of the A matrix and the sequence currents matrix. Now if we calculate A transpose times A conjugate, so AT A conjugate, we would get that that's equal to the constant 3. So I'm not going to go over all the math behind that, but if you take the transposition of the A matrix and multiply times the A matrix conjugate, you would get that that's just equal to 3. And so from that we can see then that the three-phase apparent power is going to be equal to 3 times VA012 transposed times IA012 conjugate, which of course now if we distribute the terms we will get 3 times VA0 IA0 plus 3 times VA1 IA1 plus 3 VA2 IA2. And so of course remember here that 0, 1, and 2 are the zero sequence components, positive sequence components, and negative sequence components. This doesn't mean squared or to the 0 or to the 1. Just remember that I'm using the subscript 0, 1, and 2 for 0, positive, and negative sequence quantities. And this, of course, I forgot to put it, but this should be conjugate over here. So, of course, the conjugates of the currents. So you can see that we can use the sequence components, voltages, and currents to calculate the three-phase power as well. If we had those quantities and not the phase quantities, we could also calculate the apparent power from those quantities. Now, one more thing to note here is that I'm using the A phase on all the sequence components. So for the 0, positive, and negative sequence components, I'm just using the A phase current. Now, in practical applications, you would almost always see in industry that the A phase subscript is ignored. In other words, when you talk about the 0 sequence current, you just say I0, and when you talk about the positive sequence, you just say I1, and for the negative sequence, you just say I2. But it's implied that you're talking about the A phase. Hardly ever you would see in industry that people call the positive sequence current IA1 or IB1 or IC1. You almost always use the A phase, and you use this notation, and you kind of just imply that you're talking about the A current. Now, because that's the case, you don't need a subscript and a superscript. So usually what I've seen, again, in industry is that people call the 0 sequence current I sub 0, and the positive sequence I sub 1, and the negative sequence I sub 2. These right here are by far what you would see in industry. Hardly ever you would see people talking about A and B and C sequence components. You would just see 0, 1, and 2, and again, you're just assuming that you're talking about the A phase sequence component. So I just want to point that out, because if you look at industry papers, you would probably just see I0, I1, and I2, and you might be wondering, well, where's the A, where's the B, where's the C? And really what that means is they're just talking about the A phase. That's kind of assumed, and you just say the sequence components. Alright, so next let's talk about positive, negative, and 0 sequence impedances. In this lecture, we're going to be talking about the positive, negative, and 0 sequence impedances. So far, we've only talked about voltages and currents as far as the sequence components. Now let's talk about the impedance. So when we talk about a sequence impedance, meaning a positive sequence impedance, a negative sequence impedance, or a 0 sequence impedance, what we talk about is the characteristic of a piece of equipment like a generator or a transmission line or a transformer to oppose the flow of sequence currents. So in other words, the positive sequence impedance will be the impedance that would be seen by a positive sequence current flow. And likewise, the negative sequence impedance would be the impedance that's seen by the negative sequence current flow, and the 0 sequence impedance would be the impedance that's seen by the 0 sequence current flow. And so the sequence impedances are a little bit different between the types of devices that we are taking a look at. So first, let's talk about Y-connected loads. So let me just go ahead and write it over here. This example would be for a Y-connected load. So that's, for example, as the one I've drawn over here. And I'm going to say that the phase impedance would be ZS. So that would be this resistance plus this inductance, or rather this reactance. And then this right here would be the neutral impedance, which I'm going to call C sub N. And then we're also going to define the mutual impedance between two phases. So we're going to have a mutual impedance over here from A to B. I'm going to call that ZM. Same thing from B to C. That's going to have a mutual impedance as well. And then we're also going to have a mutual impedance from A to C. So from here to here, that would be, again, ZM, the mutual impedance between any of the two phases. And of course, this impedance right here is also ZS, and this impedance is also ZS. And so the sequence impedance then for a Y-connected load is given by this matrix over here. We can say that Z012, which again is the vector of the 0 positive and negative sequence impedances, is equal to this matrix. So we would get ZS plus 3 times ZN plus 2 times ZM. And then over here on the diagonals, ZS minus ZM. And over here, again on the diagonal, ZS minus ZM. And all the off-diagonal terms are going to be zeros. So this is 0, this is 0, 0, 0, 0, and 0. And again, this would be the vector Z0, Z1, and Z2. So that's what we're going to call our zero sequence impedance, positive sequence impedance, and negative sequence impedance. Now I mentioned that the sequence impedances are going to be different for every type of device. So this would be for a Y-connected load. Now for a transmission line, so let me just go ahead and write over here, for a transmission line, we would get that generally the positive sequence and the negative sequence impedances are going to be equal to each other. And they're going to be equal to the series impedance of the transmission line minus the mutuals between the phases. Now, what's interesting about transmission lines is that the zero sequence impedance is much larger. So the zero sequence impedance of a transmission line would be equal to roughly the positive sequence impedance plus 3 times the neutral impedance. So in this case, we're going to define the neutral impedance Zn. Again, this is the neutral impedance. So let's just write it over here, neutral impedance. And that depends on the construction of the transmission line. It depends on how far the conductors are spaced between each other, if there's a ground wire on the transmission line, how far away from the ground they are, which when I say ground, I mean the literal ground, the earth essentially. So how tall the transmission tower is. So it depends on a lot of things. But one thing to note over here is that the zero sequence impedance is going to be higher than the positive or negative sequence impedances, which are also equal to each other. And from what I've seen just from industry and working on many transmission lines in the past, this zero sequence impedance is roughly 3 times the positive sequence impedance. The absolute value of that, of course. Or in other words, the magnitude of those. And this is just kind of a rule of thumb for overhead transmission line, meaning the transmission lines that you would see out in the open. I've kind of seen that just from my experience in industry, that the zero sequence impedance of a transmission line, again, an overhead transmission line, is usually 3 times larger than the positive sequence impedance, which again is equal to the negative sequence impedance for a transmission line. Now the last thing I want to talk about is generators. So for generators, again, remember that for a generator we have what's called the synchronous reactance. That's abbreviated X sub D, so that's the synchronous reactance. Then you have the transient reactance and the subtransient reactance. So XD prime and XD double prime. So those are transient and the subtransient reactance. Now for a generator, usually we ignore the resistance. I'm just going to talk about reactances for now. But let me just write it over here. The positive sequence reactance can be any of these reactances. So it can be the synchronous reactance, the transient reactance, or the subtransient reactance. And again, that depends on the time that you're looking at. So if you're looking at the instant right after a fault happens, you would take a look at the subtransient reactance. If you look a couple cycles after the fault happens, so let's say 50 milliseconds to roughly 100 milliseconds after a fault happens, you would take a look at the transient reactance. And if you're looking at steady state conditions, you would look at the synchronous reactance. And then the negative sequence reactance X2 is roughly equal to the subtransient reactance XD double prime. And the zero sequence reactance X sub 0 is equal to the leakage reactance of the generator. So X sub L, where again that's the leakage LEAKAGE reactance. So you can see that the sequence impedances depends on the type of equipment that you're looking at. If you're looking at a Y-connected load, you would get this. If you're looking at a transmission line, you would get this. And if you're looking at a generator, you would get this. But usually when you talk about doing an analysis of a power system during faults, you won't be calculating the impedances yourself. You will be given the sequence impedances and then you do your analysis based on that. But I just wanted to point out where they come from and the fact that they're different between different types of equipment. Alright, so now that we've talked about sequence voltages, currents, and impedances, let's take a look at a few examples of how we can convert the phase quantities to sequence quantities, or the other way around, sequence quantities into phase quantities. Alright, so in this example we're going to be seeing how we can convert from phase components to sequence components. So if we know the phase components, then we have the equations that we can use to convert to sequence components. So we can go from A, B, and C to positive, negative, and zero sequence currents or voltages. In this example, we're going to be taking a look at currents. So again, remember that to go from phase components to sequence components, we can use the following equations. So the zero sequence current IA, or not IA, I0, and let me actually change colors, let's do white. So I0, the zero sequence current, is going to be equal to 1/3 times the addition of all the phase currents. So IA plus IB plus IC. And in here, of course, all of these are phasors. The positive sequence current I1 is going to be equal to 1/3 times IA plus alpha IB plus alpha squared IC. And here I'm using alpha, but sometimes people use A instead of alpha, but it's the same thing. So the negative sequence current I2 is going to be equal to 1/3 times IA plus alpha squared. So notice that the positions of the alphas are changing with respect to the positive sequence current. So plus alpha IC. And again, in here, alpha, and that's sometimes called just simply A, is equal to 1 at 120 degrees. So let's use a constant that it's very convenient to use when you're converting from phase components to sequence components, or the other way around. It's basically just a phase shift of 120 degrees. And if you do alpha squared, that's going to be a shift of 240 degrees. Now these equations, a quick point that I want to make on this is that these take A phase as the reference. So A phase is reference. And this is also, so A phase is reference, and for A, B, C rotation systems. That's very important. So these equations take those two things into assumption. So we're taking A phase as the reference, and we're applying these for an ABC rotation system. If we had an ACB rotation system, then the positions of the alphas would change. So for I1, instead of being alpha on alpha times IB and alpha squared times IC, you would swap those two. So it would be alpha squared IB and alpha IC. So, but we're going to be using an ABC rotation for this example. Now, the other thing that I mentioned is that, again, we're taking A phase as the reference. What that means is that these equations apply for the following faults. So these would apply for an A to ground, a B to C phase, B to C to ground, or of course for three-phase faults. So three-phase or three-phase to ground. So again, these equations apply only for, or not apply only, but they assume that the faulted phase, if it's a ground fault, single line of ground fault, that the faulted phase is the A phase. If it's a face-to-face or a face-to-face to ground fault, it assumes that the faulted phases are B and C phases. And of course, they can be applied, of course, to a three-phase fault since those are balanced. So just a quick point that I want to make. Now, let's say, for example, let me move this up. Let's do one quick example. So let's say that, for example, let's say that we have the following phase current. So let's say that IA was equal to 100 at 5 degrees. IB was equal to 120 at minus 90 degrees. And these, of course, are amps. And IC was equal to 80 at 150 degrees. So notice a couple things here. Of course, these phase currents are unbalanced. You can see that the magnitudes of all the phases are different and the angles are not exactly 120 degrees apart. So these are what we would call an unbalanced set of phasors. And the reason that I'm doing that for this example is, of course, that we're going to be using those currents to convert to sequence components. And if they were balanced, then we would get 0 for both the zero sequence current and the negative sequence current. So just to get some numbers for both the zero and the negative sequence currents, I'm going to use unbalanced A, B, and C currents. So now we can use the equations over here at the top. So these equations over here to go from the phase quantities, which we have down here for this example, to the sequence components. So I'm just going to go ahead and plug in the numbers. Again, for I0, we have 1/3, and then that times all the three phase currents. So we're going to have 100 at 5 degrees plus 120 at minus 90 plus 80 at 150 degrees. And so if we add all of those together, we would get that the zero sequence current is equal to 25.82 at an angle of minus 66.95 degrees. And this, of course, is in amps. Now for the positive sequence current, and let's actually do the negative sequence current at the same time as well. So again, we have 1/3 times 1/3 times, and then we can see in these equations, we have 1/3 times and then 3 terms, but the first term is simply IA. So let me go ahead and plug in IA over here. So IA is 100 at 5 degrees. So I'm going to plug in that in both equations, and then plus and plus. Now for the positive sequence, we have alpha IB, and for the negative sequence, we have alpha squared IB. So alpha again is 120, and alpha squared is 240. So that times IB, which I have over here, 120 at minus 90 degrees. So 120 at minus 90 degrees. And then plus the C phase term, which again, for the positive sequence, now we're going to have alpha squared, and for the negative sequence, we're going to have just alpha. So for the positive sequence again, here I have 1 at 240 and 1 at 120, so alpha for the negative sequence current. And that times the C phase current, which is 80 angle 150 degrees. So same thing for both. 80 at 150. So now if we calculate these, and actually ran out of room over here, but if we calculate this, we get that the positive sequence and the negative sequence currents would be equal to the following number. So the positive sequence is 97.90 at an angle of 21.73 degrees. This is in amps. And the negative sequence is 4.03 at an angle of minus 110.88 degrees. And this is again in amps. Now notice a couple things here, and that's that the positive sequence has a much higher magnitude than the negative sequence, and it's still about 4 times higher than the zero sequence current as well. The reason behind that is that these phasors, although they're unbalanced, the A, B, and C phasors, that is, although they're unbalanced, they're somewhat balanced. You can see that the magnitudes are not that much different, so they're about 20% different from each other, and the angles, although they're not balanced, so they're not 120 degrees apart, they're somewhat balanced. So the difference between the A phase angle, which is 5 degrees, and the B phase angle, which is minus 90 degrees, is 95 degrees. So again, somewhat close to 120. And then the difference between the A and C phase angles is 145 degrees. So again, not exactly balanced, but not that unbalanced either. That's the reason why the positive sequence came up to be a little bit higher, or rather 4 times higher than the zero sequence current, and it's much, much higher than the negative sequence current. It's almost 25 times higher. So just a quick point that I wanted to make, just a quick observation that you can make by getting these results. Alright, so let's do one more example on how we can get the sequence components from the phase components, just to help solidify our knowledge. Now, I mentioned this before, but the same equations that we used in the previous example for the currents also apply for voltages. So for example, we can get that the sequence voltages, we can get them using the following equations. So V0, which is the zero sequence voltage, V1, which is the positive sequence voltage, and V2, which is the negative sequence voltage, are going to be equal to the following equations. So V0 is going to be equal to 1/3 VA plus VB plus VC. And again, all of these are phasors over here. So again, notice that this is basically the same equation that we used for the zero sequence current. We're just replacing currents with voltages. So the same thing applies for voltages. Now the positive sequence voltage is going to be equal to 1/3 times VA plus alpha VB plus alpha squared VC. And then lastly, the negative sequence voltage would be equal to 1/3 VA plus alpha squared VB plus alpha VC. So again, the same equations that we used before. And again, I mentioned this before, but let's mention it again. This takes a phase as the reference. And for ABC rotation systems. So for ABC rotation. Now let's do one quick example. Let's say, for example, that we had the following phase voltages. So for example, let's say that we had the following. So VA is equal to 277 at 0 degrees volts. VB is equal to 277 at 210 degrees. Or actually, let's make the VA angle 30 degrees instead. And then VC is equal to 0 volts. So this could be something like, for example, a C to ground fault where the C phase voltage collapses all the way to 0. So now, again, using the same equations, we can calculate now the sequence voltages. So V0 is going to be equal to 1/3 and then the addition of all the 3 voltages. So 277 at 30 degrees plus 277 at 210 degrees plus 0. And this gives me that VC, or rather V0, would be equal to 0 volts. And again, the reason here is that the A and B phase voltages are 120 degrees apart from each other. Now the positive sequence voltage, V1, is 1/3 times VA. So VA is 277 at 30 degrees plus alpha VB. So alpha again is 1 at 120. And again, in here, I'm simply just plugging in numbers into these equations over here. So alpha again is 1 at 120 times VB, which is in this case 277 at 210 degrees, and then plus alpha squared, which is 240 times 0, which is the C phase. So in this case, I get that the positive sequence voltage is equal to 159.93 at an angle of 0 degrees. So this right here is the positive sequence voltage. And then lastly, we can calculate the negative sequence voltage, which is going to be equal to 1/3 times 277, so VA at 30 degrees, plus alpha squared, which is 1 at 240, times VV, which is 277 at 210 degrees. And then I'm going to say simply plus 0 for VC, but again, the term is really alpha VC, but VC is 0. So if I calculate this, I get that this is equal to 159.93 at an angle of 60 degrees, and this of course is in volts, and this is our answer over here. Now again, in this case, the voltages are unbalanced, and we have the C phase voltage is equal to 0, but notice again that the zero sequence voltage came out to be 0 volts. So this would actually be a fault that does not involve ground. I think I mentioned before that this could be like a C to ground fault, but we can see from the results clearly that the zero sequence voltage is equal to 0 volts, which means that there's no fault current flowing through the zero sequence network, which means that the fault didn't actually involve ground. So that's something that you can tell from the results having the sequence components voltage. And again, the main point that I want to make here is that we can use the same equations that we use for currents. We can also use those equations for voltages. And again, remember that this applies for an ABC rotation system, and it takes A phase as the reference, meaning that these equations apply for an A to ground fault, a B to C to phase fault, a B to C to ground, phase to ground fault, or of course for three-phase faults. Alright, so we looked at examples on how we can go from phase components to sequence components. And now let's take a look at how we can go the other way around. So if we have the sequence components, how we can calculate the phase components. So sometimes we may want to convert back from sequence components to phase components. For example, often if we're analyzing a fault using the symmetrical components technique, then the results would be in sequence components, and we may want to get the actual components, meaning the phase components A, B, and C phases. So that's one case where you might want to convert back from sequence components to phase components. So let's see how we can do that. Now, we mentioned this before, but the equations for going from sequence components back to phase components are the following. So we're going to have A phase is going to be equal to the three sequence components added up together. So I0 plus I1 plus I2, and again, all of these would be phasors. IB would be equal to the zero sequence current I0 plus alpha squared I1, the positive sequence current, plus alpha I2, and then lastly IC would be equal to I0 plus alpha I1 plus alpha squared I2, and these again are all phasors. And again, I've mentioned this a few times, but it's really important. This would be a phase as reference. So reference, and for ABC rotation systems. Now, let's say, for example, that we had the following sequence components. So for example, let's say that we had the following. So we had the zero sequence current. After we've done our analysis and we've calculated the sequence components using the symmetrical components technique, we would get the following results. So let's say, for example, that we were doing that for a power system and we get the following results. So I0 is 25 at minus 70 degrees. This is in amps. I1 is 200 at 20 degrees. This is in amps. And I2, the negative sequence current, is equal to 10 at minus 110 degrees, and this is again in amps. So now, using these equations, we can convert back to the phase components. So we would get that IA, IB, and IC would be equal to the following. So they're all equal to the first term on all of the three equations is I0, so let me plug that in. 25 at minus 70, 25 at minus 70, and 25 at minus 70, and then plus, plus, plus. Now for the A phase current, we have I0 plus I1 plus I2. So let me go ahead and plug in those. So I1 is 200 at 20, and I2 is 10 at minus 110. And if we calculate this with our calculator, we get that the A phase current is equal to 196.31 at an angle of 10.42 degrees. So this is our result for the A phase. Now for the B phase, again, from this equation, now we have I0 plus alpha squared I1 plus alpha I2. So going back here, alpha squared is, again, we know that that's 1 at 240 times IB, which in this case, or rather I1, which is 200 at 20 degrees, plus alpha, so 120 times I2, which in this case is 10 at minus 110. And if we calculate this, we get that the B phase current is equal to 219.33 at an angle of minus 94.27, and this is of course in amps. So we have the B phase current now, and then we can do the same thing for the C phase. Again, going back here to our equations, IC is I0 plus alpha I1 plus alpha squared I2. So alpha, which is 120, times I1, which is 200 at 20, plus alpha squared, so 240, times I2, which is 10 at minus 110. So if we calculate this, we get that this is equal to 188.50 at an angle of 143.27 degrees. This is in amps. So again, I just wanted to show you real quick. Again, we can use these equations to go from the sequence components, which you would typically have once you've done your analysis, your fault analysis using the symmetrical components technique, to go back to phase components, which of course is helpful because that's actually what a relay sees. It sees the phase components. So you can go from sequence components, I0, I1, and I2, so 0, positive and negative sequence currents, back to the phase components, so the A phase, B phase, and C phase, using these equations over here as we've shown in this example. Alright, welcome back. So I mentioned this before, but the same equations that we use for currents also apply for voltages. So we can use the same equations to go from sequence voltages back to phase voltages. So in other words, we can use the following equations. If we had the sequence voltages, we could calculate the phase voltages, so VA, VB, and VC, using the following equations. So VA would be equal to all the three sequence voltages added up together. So V0 plus V1 plus V2. VB, on the other hand, would be equal to V0 plus alpha squared V1 plus alpha V2. And then lastly, VC would be equal to V0 plus alpha V1 plus alpha squared V2. So again, if you recall from the current example, so the previous example, we used similar equations for currents. We're essentially swapping currents for voltages, but we're using the same terms. So now let's say, for example, let's do an example real quick. So let's say, for example, that we had the following sequence voltages. So we have V0, V1, and V2, which were equal to the following. So V0, the zero sequence voltage, is equal to 0 volts. V1, the positive sequence voltage, is equal to 200 at 10 degrees volts, and the negative sequence voltage is equal to 200 at 120 degrees. This is in volts. And again, you would have these results once you've done a fault analysis using the symmetrical components tool, or the symmetrical components technique. And now you might want to go back from sequence components back to phase components. So again, using these equations, now we can calculate VA, VB, and VC over here using, again, these equations over here. So VA is simply the addition of all three. So we're going to have all three sequence components, that is. So we're going to have 0 plus 200 at 10 degrees plus 200 at 120 degrees, which is equal to 229.43. And let me rewrite this. So 3 at an angle of 65 degrees. This is in volts. And then VB would be equal to 0 plus alpha squared, so 1 at 240 times 200 at an angle of 10, so VB plus 120 times 200 at 120 degrees, and this is going to be equal to 398.48 at an angle of minus 115 degrees. And then lastly, VC, let me move this up a little bit more. So this would be equal to 0 plus alpha, so 1 at 120 times 200 at 10 degrees, so VB, plus 1 at 240, so alpha squared, times VC, which is 200 at 120. And if we calculate all of this, we would get that the C phase voltage is equal to 169.05. And let me rewrite this. This should be a 5 at an angle of 65 degrees. So now we've calculated all the three phase voltages from the sequence voltages over here using these equations over here. So again, the main point that I wanted to make here is that we can use the same equations that we used for currents for voltages as well. The same equations apply. Alright, so let's talk about how we can use the symmetrical components technique to calculate or analyze single line to ground faults. So the key in performing fault to calculate. Alright, so let's talk about how we can use the symmetrical components technique to calculate or analyze single line to ground faults. So the key in performing fault analysis by using the symmetrical components technique is to decompose the system into the sequence networks, which are independent of each other, and then we can use the sequence networks, or rather we can interconnect them depending on the type of fault. So for example, let's say that we have the system over here that I have on the top left, which is the same one that we looked at before for the three-phase fault example. So in this system, again, we have the system equivalent, a transformer that's connected in delta Y configuration. And let me actually put that over here. So this is connected in delta Y configuration. And we have a feeder. And we've been given the data for the system and the transformer at 100 MVA base and for the feeder at 35 MVA base. Now, a couple of things that I want to mention here is that, and let me actually write them over here. For generators, the positive and the negative sequence impedances are going to be the same, but the zero sequence impedance is not going to be the same. So again, we need to basically but input the positive, negative, or zero sequence impedance for every equipment in the power system independently. So they might or might not have the same impedance. So again, for generators, the positive and the negative sequence impedances are the same, and the zero sequence impedance is not the same. Now for transformers, XT, or actually let me write it as X1, the positive sequence impedance is going to be the same as the negative sequence impedance, which is going to be the same as the zero sequence impedance. In other words, the impedance that we're going to be using for a transformer in the positive, the negative, and the zero sequence networks is going to be the same. Now, the connection of that transformer to the rest of the sequence networks is going to depend on the connection of the transformer. So for example, if we have a delta Y grounded transformer like we do for this example, that's going to affect how we connect the transformer impedance within the sequence networks. Now, the value of the transformer impedance, though, is going to stay the same. And then lastly, for feeders, so I'm going to say for feeders / T lines, so transmission lines, the positive and the negative sequence impedances are the same, but they're not the same as the zero sequence impedance. So similar to a generator, again, the zero sequence impedance is going to be different for feeders or transmission lines. Usually the zero sequence impedance is a little bit larger than the positive or the negative sequence impedances. Now again, the point that I'm trying to make here is that every component in the power system, so whether that's a system equivalent, a transformer, or a feeder, is going to have a positive sequence impedance, a negative sequence impedance, and a zero sequence impedance. And then we can use those to build what's called the sequence networks. And then we can interconnect the sequence networks as we need to, depending on the type of fault. So as we're going to see, the sequence interconnections are going to be different for every type of fault. So for example, let me move this up a little bit. let's say that we had a system, and for that system we've derived the sequence networks. So in other words, we had the positive sequence network over here, so positive, the negative, and the zero sequence networks. And then we're going to have what's called the neutral of each one of those, so N1, N2, and N0. Now in a power system, we have positive sequence voltage sources. So the generators are generating voltages in the positive sequence, which is or rather has the same phase rotation as the system. So again, remember that the positive sequence network and positive sequence quantities have the same phase rotation as the actual power system. So if we have an ABC rotation power system, the phasors within the positive sequence network are going to rotate in the same direction. The negative sequence network rotates in the opposite direction, and the zero sequence network has the same phase angle between all three phases. So the reason I mention that is because we're always going to have a source in the positive sequence network. So for example, we could say then that our positive sequence network is going to look like this. So we have a source over here, and then we're going to have some positive sequence impedance that we're going to derive, or rather that we're going to build from our system. And then we're going to have the same thing for the negative and the zero sequence network. But again, notice here that for both the negative and the zero sequence networks, we don't have a source. And the reason for that is that, of course, generators do not generate negative or zero sequence voltages. So they're not a negative or zero sequence source. Now, of course, that would be under normal conditions. So once we've built the sequence networks, again, these are what we're going to call the sequence networks. They're all independent of each other. And so what we need to do for the symmetrical components technique is we need to interconnect those sequence networks depending on the type of fault. So we're going to begin by talking about a single line of ground fault. And for single line of ground faults, let's say that we had a fault on this feeder over here, or rather on this bus over here. So this is the fault location in our system. Then if that's the case, for a single line of ground fault, we're going to interconnect these sequence networks in series. So in other words, we're going to make a connection like this. So they're all in series with each other, and then back to the positive sequence network. So here, of course, this would be the positive sequence current I1, negative sequence current I2, and zero sequence current I0. So the point that I'm trying to make here is that once we've built the sequence networks, we need to interconnect them based on the type of fault. And for a single line of ground fault specifically, we're going to interconnect all the three sequence networks in series with each other. And again, this right here is the point of the fault. So we're interconnecting at the point of the fault. So you can see that I've connected this point over here, which is the point of the fault, back to the neutral of the negative sequence. And then same thing between negative and zero and positive. All right, so next let's take a look at an example on how we can calculate the phase currents for this example power system for a single line of ground fault at bus Y. All right, so now that we know how to interconnect the sequence networks for a single line of ground fault, let's take a look at this practical example. So again, we have the example power system here where we have a system equivalent, a transformer, and a feeder, and what we want to do is we want to calculate the fault current for a fault at bus Y. So a fault current, or rather a fault over here at this bus. So let's see how we can do that. So the first thing that we need to do is we need to convert everything to a common base. So I'm going to say that step 1 in our 6-step process is going to be to convert to a common base. And again, we did this for the 3-phase example, but let's go ahead and do it again. So convert to a common base. So in here, of course, we have both the system and the transformer at 100 MVA base, but we don't have the feeder on that same base. So the feeder base is at 35 MVA. Now we derived this before, or rather we calculated this before in the 3-phase example, and we said that if we converted C1 XY to a 100 MVA base, we got that number was 0.286, and of course the angle stays the same, so at 85 degrees in per unit. Now we can see from here that the zero sequence impedance is basically 3 times that of the positive sequence impedance. So what I can do here is I can say Z0XY, which is the zero sequence impedance of the feeder, is essentially going to be this number multiplied times 3. So if I do that, I get that Z0XY is going to be equal to 0.857, and again the angle stays the same, so 70 degrees. And this again is in per unit. So now again, these are the impedances for the feeder at 100 MVA. So what we've done is we've converted these impedances, which were at 35 MVA, and we've converted those to 100 MVA. So now we have everything on the same base. So let me move this up a little bit. And now I'm going to say, well, step number 2, and let's go ahead and switch colors. So step 2 is going to be to draw the circuit. So draw the circuit. So essentially we're going to have the following circuit. So again, we have the system over here. We're going to have an impedance for the transformer, or rather for the system. So this is going to be X1S or X2S. So either the positive or the negative sequence impedance for the system, which in this case was J0.12 per unit. And again, I mentioned this before, but this source is going to be 1 at 90 degrees per unit. So then after that, if we take a look at this system over here, then we have the transformer and then we have the feeder. So we're going to have those impedances on our circuit over here. So we're going to have the transformer impedance over here, and I'm going to call those X1T and X2T and X0T. Again, remember that for a transformer, the positive, negative, and zero sequence impedances are all the same. And so those are, again, we can see that from here, from the data, that's 8%. So in other words, J0.08 per unit. And then lastly, we're going to have the feeder impedance. So that's going to be either Z1XY or Z0XY. So either the positive or the zero sequence impedances. And again, the positive is the same as the negative for a feeder or a transmission line. And so that was 0.286 at 85 degrees per unit. And the zero sequence impedance is this one that we calculated over here. So that's 0.857. So let me move this up. 0.857 at 70 degrees per unit. And here is where we have the fault. So again, we're faulting bus Y on this example power system over here. So here's where the fault is. So now we have our circuit, but again, we need to decompose this into the different sequence networks, because again, we have different impedances for the positive, negative, and zero sequence networks. So what we need to do then is we need to, again, decompose this circuit. So let me put it over here. I want to say decompose into the sequence networks. So into sequence networks. So essentially what I'm saying is now we're going to take the actual impedances for each one of the sequence networks independently. So now we're going to have here N1, and let me actually switch back to white because we're going to be using this in other examples. So N1, again, we're going to have positive sequence network over here. We have the neutral that, of course, we're going to have a positive sequence voltage source. So we have our voltage source over here, which is at 190 degrees per unit. And then again, we have the system impedance, transformer impedance, and feeder impedance over here. So this is the system, and that's actually a reactance. So that's J 0.12 per unit. Then we have the transformer X1T that is equal to J 0.08 per unit. And then lastly we have the feeder, so Z1XY, that's equal to 0.286 per unit and at an angle of 85 degrees per unit. Then we have to do the same thing for the negative sequence network. But again, notice here that for the system, the positive and negative sequence impedances are the same. Same thing for the transformer, and same thing for the feeder. So what I'm going to do here then is I'm just simply going to make a copy of this whole thing. And let's make a copy of that, paste it here. And this is going to be our negative sequence network. So it's essentially the same as the positive sequence. Again, that's just from the fact that the impedances are the same, but this technically would be X2 over here. So we're going to have X2S, X2T, and Z2XY. And then lastly, we have the zero sequence network over here. But now notice here that the transformer is connected, and I forgot to put it over here, but it's connected delta on the high side. So the effect that that has is that it blocks the flow of zero sequence current. So when we come here to our sequence network, we're going to have the same system impedance over here, transformer impedance, and feeder impedance. But because we have a delta connection on the high side of a transformer, so over here, again, that blocks the flow of zero sequence currents. So in our zero sequence network, then we essentially have an open circuit over here such that the zero sequence system impedance basically doesn't come into effect or doesn't come into play. So we essentially have a straight connection from here to here, and we ignore the zero sequence system equivalent, or rather system impedance. Now here I noticed that I made a copy of this, but I meant to delete the source because again, we don't have a source for the negative sequence network since we don't have a source of negative sequence voltage. Alright, so now we have our sequence networks, and let me actually put the numbers over here. So X0T is the same, J 0.08 per unit. And the zero sequence feeder impedance, we calculated that over here. That's 0.857. So this is equal to 0.857 at 70 degrees in per unit. So now we have our sequence networks. And I'm going to do one more step. So we're going to have step 3 now. Let's do blue. So step 3 is going to be to simplify the networks. So simplify networks. So essentially what I'm saying here is that notice that here that for the positive sequence network we have 3 impedances, same thing for the negative sequence network, and for the zero sequence network we have 2 impedances. So I'm going to combine all of those impedances to have a more simple system. And let me switch back to white. So we're going to have essentially, again, the neutral of the positive sequence network over here. We're going to have a positive sequence voltage source. So this is going to be 1 at angle 90 degrees per unit. And we're going to have a positive sequence impedance over here. We're going to have the same thing for the negative sequence network. So N2 over here. Just simply 1 impedance for the negative sequence network, and same thing for the zero sequence network. So we're going to have just 1 impedance over here. Alright, and then here of course, this right here is the location of the fault. So what I'm going to do in this step then is I'm basically just going to combine these 3 impedances, these 3, and these 2. So I'm going to add them up, or add them all up together, so that I get a more simple circuit. So if I do that, I would get that my simplified zero sequence, or our positive sequence impedance Z1, which again is equal to X1S plus X1T plus Z1XY. That's going to be equal to 0.486 at an angle of 87.057 degrees, and that's in per unit. Same thing over here for the negative sequence network. I'm going to have Z2, which is going to be equal to X2S plus X2T plus Z2XY, and that's going to be the same number. So 0.486 at an angle of 87.057 degrees. And then lastly, for the zero sequence impedance, I'm going to have Z0, which is equal to simply x0t plus z0xy, and that's going to be equal to 0.933 at an angle of 71.681 degrees. So now I have a very simple network. So let me go to step 4 and let's switch colors again. So step 4 is going to be to interconnect. So interconnect the sequence networks as needed. So interconnect as needed for the type of fault. So again, this is going to vary dependent on the type of fault that we have. For this example, we're going to do a single line of ground fault. And let me actually redraw this again. So I'm going to have again positive sequence over here, positive sequence voltage source, one simple impedance. That impedance has a value of 0.486 angle 87.057. That's in per unit. This is our faulted bus. I want to have the negative sequence over here. So same thing, just one simple impedance. That's going to be equal to Z2, which is equal to 0.486 angle 87.057. And then lastly, the zero sequence over here. And that's going to be equal to Z0, which is equal to 0.933 angle 71.681. Alright, so now again we have a very simple sequence network, and again this right here is the faulted bus. So same thing over here, same thing over here. So now again in step 4 what we're going to do is we're going to interconnect the sequence networks however we need to. For the case of a single line of ground fault, we're going to connect all three in series. So this is going to be connected in series with this, so positive in series with the negative, negative in series with the zero, and then from the zero back to the positive sequence network over here. And in here, of course, our positive sequence current flows this way, negative sequence flows this way, and zero sequence flows this way. So now we can go one more step, and we're actually going to have two more steps. So let me go back. Let's do maybe gray. So step 5 is going to be convert to actual quantities. Or actually I skipped one step over here. Let's go back. And now that we have this simple circuit for the sequence interconnections, we can actually calculate. So I should say over here, interconnect as needed for the type of fault and calculate. So now if I go back, let's do white over here. So now I can calculate my currents, right? So I have that, I know that I1 is going to be the same as I2 is going to be the same as I0. The reason behind that is that I1 flows this way and it flows over here, but you can notice that of course then we have I2 flowing in the negative sequence network. So essentially I1 is going to be the same as I2. Same thing over here, we're going to have I2 flowing this way, so I2 and I0 are the same. So again I can say here I1 is equal to I2 is equal to I0, which is going to be equal to 1 angle 90, so the source on the positive sequence network divided by all the three impedances, right? Because we have all of them connected in series. So I can simply add the impedances over here, Z1 plus Z2 plus Z0. So this is going to be equal to 1 angle 90 per unit, now divided by all the impedances. So we're going to have 0.487 angle 87.057. This is the positive sequence impedance. Same thing for the negative sequence impedance. So 0.487 angle 87.057. And then lastly, the zero sequence impedance, which is equal to 0.933 angle 71.681 degrees. So if I calculate this, I get that the positive sequence, which is the same as the negative sequence, which is the same as the zero sequence, again, for a single underground fault specifically, that's going to be equal to 0.529 at an angle of 104.647 degrees in per unit. So this is our answer again. That's I1, I2, and I0. Alright, so now that we have the sequence current, now we can calculate, and we have them in per unit, now we can calculate them or convert them to actual quantity. So that's what step 5 is going to be. So let me just write it over here. Step 5 is going to be convert to actual quantities, because again here we have the answer but in per unit, not in amps. And of course we want our answer in amps. So for this case, the base current, again, remember that that's equal to the base power divided by square root of 3 times the base voltage. So I want the answer right at the location of the fault, which in this case was bus Y over here, which is at 13.8 kV. So I'm going to use that for my base voltage. And here coming down, again, we used 100 MVA ST base power. So 100 times 10 to the 6 divided by square root of 3 times the base voltage, which is 13.8 times 10 to the 3, so 13.8 kV. And this is equal to 4183.698 amps. So now I can convert this answer, which was in per unit, to actual quantities. So I can say again here that I1, for example, is going to be equal to, again, this number over here, 0.529 times 4,183. So if I calculate that, that gives me that the positive sequence current in amps is going to be equal to 2,213.176 at an angle of 104.647 degrees. This is in amps. Same thing for the negative sequence current. So 2213.176 angle 104.647, and of course same thing for the zero sequence. So 2213.176 angle 104.647 degrees. This is all in amps. So now again we have the answers for the sequence currents in amps. Now I mentioned this before in the example where we converted from sequence currents to phase currents, and that's that now that we've done our analysis, the answers are in sequence currents, but of course you might want them in phase components. So step 6 then, we can say, let me switch colors, we can say that step 6 is going to be to convert to phase quantities. So convert to phase quantities if needed, of course. So then we can say, again, we know this from before, we did an example, but IA is equal to I0 plus I1 plus I2, which again is the same as saying 3I0, right? Because I1 is equal to I0, I2 is also equal to I0. So in this case, for a single line of ground fault, IA is going to be equal to 3I0. That's ignoring load and ignoring a networked connection. But IA for this example is going to be 3I0. And that's why sometimes you'll see in protective relays that they call the ground current a 3I0. The reason behind that is that for a system like this, once you do the analysis using the symmetrical components technique, you'll see that the phase current for the faulted phase in a single line of ground fault is actually going to be equal to 3 times the zero sequence current, so 3I0. That's where that comes from. So in here then I would get that IA, which is the faulted phase in our single line of ground fault example, is going to be equal to 6639.528 at an angle of 104.647 degrees. So this is our answer for the fault current at bus Y in our example power system over here in the top left. So one more thing that I want to show you is, of course, that we can do the same thing for IB and IC. We can use the equations that we used before to go back from sequence components to phase components. And so for IB, we get that that's equal to I0 plus alpha squared I1 plus alpha I2. IC is equal to I0 plus alpha I1 plus alpha squared I2. And if you plug in the numbers, you'll see that these two come out to 0. And of course that makes sense because we have an A phase to ground single line of ground fault. So the unfaulted phases don't have any current. This is of course ignoring load prior to the fault. But again, we'll see that of course we have a large fault current for the faulted phase. And the other two have 0 amps as the magnitude. Alright, so we're going to be using this same example to calculate the fault currents for line-to-line faults and double line of ground faults at bus Y as well in the next lectures.